Hey, welcome back, Mr. Warnow here. I'm going to go over a radius and interval of convergence question with you. Radius and interval of convergence is just basically saying we want to find a domain and range that guarantees that this series will converge by using any of our known tests. So when we do a radius and interval of convergence, we're going to use the one test that can guarantee it, and that's going to be our ratio test. The ratio test says that if we take the limit as n goes to infinity of the next term and divide it by the original term a sub n, as long as it's less than 1, we know that this will converge. So we're going to apply the ratio test for this. So let's go ahead and do that. When we take the limit as n goes to infinity, we're going to use absolute values. These become very important for us because we only want the magnitude as it's approaching infinity. And the nice thing about the magnitude is we really don't have to worry about the -1 to the n, the alternating part here. And that is because it's going to become positive once we take it out of the absolute value. So I only have to worry about these other ones. So I got n and I have n plus 1. So when I rewrite this, when I get my next term, my a sub n plus 1 term, all I'm going to do is I'm going to replace each n with n plus 1. So we get this x minus 2 to the n plus 1 plus 1, and that becomes then just n plus 2 over 3 to the n plus 1 and times n plus 1. Now there is my next term, a sub n plus 1. We're now going to divide that by the OG, the original function, the original series. And to do that, I'm just going to invert this right here. I'm going to divide by it, but if I invert and multiply, it's the same thing. So we can get this 3 to the n times n over, this becomes x minus 2 to the n plus 1. Now mind you, this has to be less than 1 right there. Make sure you write that down. So when solving this, we're going to simplify this, the limit as n goes to infinity. I got this x minus 2 to the n plus 2, and I got this x minus 2 to the n plus 1 on bottom. If I subtract the exponents, I'm going to wind up with 1 x minus 2 on the top. So I'm going to go ahead and write that, x minus 2 on the top. So those are gone. Next I have this 3 to the n and this 3 to the n plus 1. Again, if I subtract the exponents, I'm going to wind up with a 3 on bottom. Hint, I have more 3's on bottom. How many more? Only 1 more. 3 to the n, this is 3 to the n plus 1. I have an extra 3 on bottom, so that's just going to remain with a 3 on bottom right there. So those are gone. Lastly, I have this n and this n plus 1 right here. And unfortunately, we can't simplify those, so we are going to leave them. N on top, n plus 1 on bottom, and that still is less than 1. When we're solving this, here's what we want. We're taking the limit as n goes to infinity. So if it does not have an n, I can factor it to the outside right here. So we're going to cash this thing outside. And that's going to leave us with the absolute value of x minus 2 over 3. We're going to keep the absolute value because we're just rewriting it. I don't need it over the 3 because 3 is already positive. I need it on the x part because x can be positive or negative still, so we need it for the top only. This is going to be times the limit as n goes to infinity of this n over n plus 1, and that's still less than 1. And this is actually what we want. It looks a mess, but we know limit rules. If we let n go to infinity, the inside of here just goes to 1. We just look at what matters the most, the n over n, and we can use our ratio. Because the degrees are the same, we look at the ratio of the coefficient in between them, and that is just 1 right there. So this whole limit right here just becomes 1. And what we're left with, I'm going to write over here, is the absolute value of x minus 3, whoop, that's what we're looking to, 2 is less, and I'm going to multiply both sides by 3. And this is golden right here. This is the most important part right there. Because here's what it says. Right here is the center of our system. That's the center of our polynomial, of our Taylor series right here. The 3 here, if you know anything from algebra, when you look at an absolute value is really a distance. We're saying that the distance from the center is less than 3. 3 is what we call the radius. So we have a couple things here. One, we have our center, which is 2, and now we have our radius, which is 3. What this says is if I put 2 in the middle, I can go 3 units in either direction. That's going to put me at 5, or if I go the other way, it's going to put me at -1. And what this guarantees is if you pick any number between -1 and 5, this series will converge. So in other words, if you pick pi, this series will converge. We can use our tests to prove it will converge for us. But here's the problem. Because of the ratio test, this less than 1, a less than 1 doesn't guarantee the endpoints. And that's the problem, because if it's equal to 1, it's inconclusive. We saw that with the ratio test in another previous video. So we need to make sure that these endpoints will work or they don't work. And this is the hard part. All right, so what we're going to do next is check the endpoints. We have to check our endpoints. And this is the part that most students always forget. My first endpoint is this -1. Plug it into the original series, n equals 1 to infinity. This becomes -1 to the n. And this will become -1 minus 2, a -3 to the n plus 1 over 3 to the n times n. I'm going to simplify this a little bit right here. This becomes -1 to the n. This is very complicated. This becomes -1 to the n plus 1 times 3 to the n times 3. Whoop, that's what we're looking through. So I just expanded this whole thing. Take a minute and verify that that is going to be true for us.
I'm having trouble with the connection. Please try again later.
So we're going to divide that by 3 to the n times n. And let's see what happens. The 3 to the n's will cancel. And what I'm left with is the following. I have this -1 to the n, -1 to the n plus 1. That's just -n to the 2n plus 1 times 3 over n. And this 2n plus 1 is always an odd number. That's the definition of an odd number for us in math. So this is always just going to be a negative. I can just factor out that negative. N equals 1 to infinity, 3 over n. And now we look here. That's a p series, so this will diverge by p series. So here's what we know. X equals -1 does not work for us. So a lot of work for that. But we're not done because we have another endpoint to check, and that's the 5. All right, let's cook. I'm going to erase this, so let's go check 5 now. So the next endpoint we're going to check is x equals 5. Plug it into the OG, -1 to infinity, -1 to the n. 5 minus 2 is 3, so I get 3 to the n plus 1 over 3 to the n times n. And let's see what happens here. I'm going to clean this up a little bit. N equals 1 to infinity, -1 to the n. This becomes 3 to the n times 3 to the first over 3 to the n times n. And those cancel again. And what we're left with is the following. N equals 1 to infinity, -1 to the n. Notice there's no more negatives like there were before, and I get 3 over n. And even though it looks like p series again, this is an alternating series right here. So if I take the limit as n goes to infinity, 3 over n, that becomes 0. So this will converge by an alternating series. So we would say the series alternates decreases in magnitude, and the limit equals 0. Therefore, this is going to converge by alternating series. Boom. So, -1 didn't work, but 5 checks out. So now we have our interval of guaranteed convergence. And we're going to write that up here. So for our interval, we're going between -1 and 5. -1 doesn't work, so I'm going to leave it open, empty over here, but the 5 does work, so I have to include it. And there's all of our answers right there. Welcome to the hardest question you're going to answer in calculus right there. Radius and interval of convergence. I hope you guys enjoyed the video. I'll see you later. Bye-bye.